Okay, I'm here ready to talk about further topics in Chapter 4, and in particular moving on to the asymmetric waveguide. And so far we've studied the symmetric waveguide, and it turns out that the symmetric waveguide has a particularly simple mathematical solution that we can actually deal with, although it might not have seemed so simple with that tangent function and those solutions, but we could actually deal with it. For the asymmetric waveguide, it's a different story, and in the asymmetric waveguide we've got a situation something like this, where we've got a core index of n1 and two different cladding indices of n2 and n3. And what we'll do is we'll suppose that n1 is larger than n2, and n2 is in turn larger than n3. So now n2 and n3 are not equal, and we have our asymmetric waveguide. So there's different indices on both sides of the waveguide. And what that means is that we've got different critical angles on both sides. So because n2 is larger than n3, the critical angle for n2 will be larger than the critical angle for n3. So maybe we could write that the critical angle for critical number 2 there, whereas on the other side of the waveguide we have a critical angle n3, which is smaller. So maybe we'll write it, I think I'm exaggerating, theta C3. Okay. In any case, the mathematics is that since n2 is greater than n3, this implies that theta critical number 2 is greater than theta critical number 3. Okay. And so if we have theta, the incident angle of a zigzag ray, greater than theta critical 2, then that implies we get total internal reflection at both sides. And that's good. We then can guide, so then we have guided modes. If, on the other hand, the zigzag angle of a ray is in between these two critical angles, theta critical 2 is greater than theta, which is greater than theta critical 3, then we have a problem. We get TIR only on the N2 side. Okay, in which case we don't have guided, so light energy leaks out or escapes on the N3 side. Okay, so that's the basic idea of an asymmetric waveguide. What I can do is make a plot of the index versus, say, the y coordinate. Maybe we'll take the z coordinate to be the direction of propagation, and the y coordinate to be perpendicular to that. So this is the profile of the index profile. So n1 is larger than n2, which is in turn larger than n3. And I suppose that this crossing point is not n equals 0. So we have our waveguide where we have n3 on one side, n1 in the core, and then n2 on the other side. And so this is the core of the waveguide here. Okay. It turns out then that the modes, and I'll try to draw them directly underneath here, the modes then look asymmetric. Whereas with the symmetric waveguide, the modes themselves were symmetrical, I'll just sketch out the first two modes here for this waveguide. And over here, let's see, I've got N3 on the left. And so there's more of a barrier to having the electric field penetrating on the N3 side and less of a barrier for it to penetrate on the N2 side, because N2 is closer than N1. And so we get something, a mode that looks at least schematically like this, where we have greater penetration over on the N2 side. Okay, so this is the N2 side. And then we could also make a similar picture showing the next mode up, and again showing greater penetration of the electric field on the N2 side. So now our modes are asymmetric. The other implications for this, as far as we're concerned, and really we're not going to work with the mathematics of this too much. Certainly the main implication is that you've got to satisfy the zigzagging angle being larger than the largest of the critical angles. And it turns out that other results are that one, TE and TM mode plots look different now. Whereas in the symmetric waveguide, we couldn't tell the difference. And in fact, the TE and the TM mode plots were identical, but now they differ slightly due to the asymmetry. The other result or consequence of this is that the M equals 0 mode no longer has D equals 0 cutoff. You'll recall that, perhaps I can bring the picture up here, when we drew the mode plots for the symmetrical waveguide, we always had our M equals 0 mode with a cutoff right at D by lambda is equal to 0, or D is equal to 0. And that's no longer the case with the asymmetric waveguide. Okay, so and what that means practically is that for the symmetric waveguide, no matter how thin the waveguide, your 0th order, your M equals 0 order mode, will exist. Whereas for the asymmetric waveguide, the cutoff may be 0, maybe the cutoff is above 0, and so it's possible to have D less than the cutoff, in which case no guided mode will exist. Okay, I think I'll stop there. That's a slide about the asymmetric waveguide.